Hello everyone, welcome back to the MongoDB exploration journey. I'm Keshav and I work as a principal engineer. In our previous tutorial, we covered the basics of MongoDB, right from understanding what MongoDB is, its documents, collection, the BSON, the transactions in the MongoDB and the indexes in the MongoDB. Today we'll continue our deep dive into the MongoDB universe and we'll focus on advanced topics like sharded cluster architecture, the shard keys, the storage engines, which include right from the memory map world to the WiredTiger architecture and now the clustered collections. We'll also discuss the considerations for when to use MongoDB and based on the various workload scenarios, how to fine-tune it. So let's dive right into the world of MongoDB's sharded cluster. Think of the sharded cluster as MongoDB's answer to handling massive data sets with ease. As you can see in the diagram, there are shards, there are Mongos and config servers, and these are the key components. The shards contain the subset of data and can be deployed as replica sets for data redundancy. The Mongos act as a query router, facilitating the communication between the client and the sharded cluster. And the config servers store the crucial metadata and configuration settings for the entire cluster. Hence, the query starts coming from here, and based on the config server, it will know which shard to hit. As you have learned in the basics, data in the MongoDB is organized into collections. Now with the sharded clusters, we take our scalability to the next level by sharding the data at the collection level, and it will effectively distribute the data into the various shards across the cluster. So let's see what are the shard keys. The shard keys are our secret sauce for optimal data distribution. These keys, composed of one or more fields in the documents, are instrumental in distributing collection documents across the shards. To shard a populated collection, it must have an index. MongoDB, it's very clever enough, and it will create a supporting index in case there is no appropriate index for the specified shard key. So let's say I have a shard key S1 and I don't have an index, so there is no index from S1, like any index starting from S1. What MongoDB will do is it will automatically create an index that starts with S1. Generally, the ID field is your shard key, and of course there is an index as we had seen earlier with the underscore ID field. The choice of shard key is not arbitrary. It plays a pivotal role and it will impact the performance, efficiency and scalability of our MongoDB cluster. It is a strategic decision that also influences the overall sharding strategy. If we have a shard key that is very memory intensive, and since the indexes are maintained in memory, it will create a lot of problems and impact cluster performance. Now let's deep dive into the further concept of chunks. These are the building blocks for our sharded data. A chunk consists of subset of sharded data, each with an inclusive lower and exclusive upper based on the shard key. So each shard would have these chunks, and shard would remain in a single node. So if you see the hierarchy, you'll have a collection which can have 100 documents, and it can be distributed in 3 nodes: node 1, node 2, node 3, and each node would have chunks. So maybe each node would have 33 documents, and let's say 11 documents in a chunk. MongoDB splits chunks when they grow beyond the configured chunk size. So there would be a chunk size, and in case it grows beyond it, so there would be a splitting. It is essential for MongoDB to actually maintain this optimal number, and it prevents any shard from becoming overloaded. The smallest range of a chunk can only represent one document. So at the least, a chunk can have only one document, and we cannot break a document into multiple chunks. This introduces an interesting aspect to our chunk management, and it will ensure that our chunks are handled intelligently to maintain the efficiency. Now let's delve into the intricacies of storage engines. Specifically, we'll go over with the memory map, and then we'll explore the transition to the WiredTiger. As we all know, a database storage engine plays a pivotal role in the performance, concurrency, and overall efficiency. So let's dive into the details of it. First up, let's see what memory map is. So MongoDB's original storage engine, memory map, took an approach wherein BSON documents were directly mapped into memory using memory mapped access. In memory map, BSON documents were stored on disk in an uncompressed manner. So these documents were uncompressed. Each document had its own disk lock, and it was identified by a 32-bit integer representing the file plus the offset. So there was an ID that was referring to a disk lock using the B+ tree, and this disk lock was 32-bit integer representing which file the document was and the offset in the file. The disk lock operation is generally O1 operation. However, the memory map had certain limitations. The first and the foremost one was that the lock for the write operations was at the global DB level. So any one write operation would have the entire DB locked up, and this was a significant bottleneck for the writes. To address this, the memory map actually evolved by removing this DB lock into the collection level lock. Despite this improvement, the MongoDB decided that we should move to a more advanced storage engine since it was not able to fulfill the write operations or the write efficiency. So in version 4.0 of MongoDB, the map was deprecated, and it made way for the more scalable storage solutions. And fast forwarding to 2014, MongoDB made a substantial leap by adopting WiredTiger as its default storage engine. This transition marked a pivotal moment in the MongoDB's evolution, addressing the limitations that memory map had, and it introduced a lot of new features. The key features were the MongoDB now had document level locking. So instead of locking the collection, it was now locking just the document, which means you can have multiple writes happening to the same collection. It also introduced compression. So compression was actually needed to store more data in a cluster or in a node, and that's where it solved that problem, and hence the cost of storing the data decreased significantly, and it improved the concurrency. So WiredTiger actually improved the support for multiple concurrent read and write operations, and this was actually beneficial for heavy write loads. Generally the reads were faster, but we wanted, or the MongoDB wanted, that the writes also become faster. However, there were certain issues as well. The lookup process in MongoDB was one of them. Retrieving documents in the MongoDB now became two-step process. First, MongoDB used to search for the ID. We used to search the record ID. So there was a B+ tree in memory to look up the record ID, and again there was another B+ tree in memory that from where the record ID was actually used to find the actual document. So instead of now storing one B plus tree, there were two B plus tree in memory per collection, which resulted in increase in memory consumption. Also, it increased the CPU, as now you have to do two lookups instead of one. However, it also allowed MongoDB for the collection level logs, and this increased the write efficiency overall. Now let's explore a more recent development in the storage engine world for MongoDB, which is the clustered collections architecture. It was introduced very recently in June 22 in the MongoDB 5.3 version, and this feature added a new layer to our understanding. In this architecture, the primary index again becomes the clustered one, and it will store all the fields for the document. So you don't have two lookups. Instead, now it's one lookup. So the ID is directly referencing the document. This actually reduces the memory consumption, plus reduces the CPU, as well as has all the benefits of having the document level lock plus increase in write efficiency. So you can think of it as a fascinating evolution resembling the MySQL's InnoDB storage engine, but in the NoSQL world, which provides you with flexibility of the way you want to store the data in a JSON or basically BSON format. Now let's address a very fundamental question that we all have: when we should use MongoDB. So MongoDB is a very powerful NoSQL database, and it is well suited for both read heavy and write heavy operations now, but its performance characteristics and considerations may vary on specific workload and use case base. So here is a summary that I've created, wherein it can tell you how or when it can be used for the read heavy operations and how it can be used for the write heavy operations. In the read heavy operations space, MongoDB actually supports indexes, and it will allow efficient execution of read queries by minimizing the number of documents that can be scanned. So you can have multiple indexes, which will help you to reduce the number of document scans and find the documents much faster. Also, the query performance also increases with appropriate indexing, and hence the read operations will improvise significantly. The aggregation framework in the MongoDB world enables complex data transformations and analytics, and it will hence increase the read capabilities. So the aggregation is similar to the count star in SQL world, and this will increase the read capabilities, and this actually increases because now we have a B plus tree, and if you remember in the chunk world we always have the lower and the upper bound, so you can consider this thing as a segment tree. In the write heavy operations, now in the WiredTiger storage engine or in the clustered collections architecture storage engine, the concurrency is at the document level. So that means I can lock the document, but I can write to multiple documents in a collection, and this will improve my write operations efficiency across the collection, which was earlier a problem in the MongoDB world. The horizontal scalability or the sharding capabilities of MongoDB enable write intensive workloads, since the data is now sharded across multiple nodes, and hence each node would have its own capability of writing the data into the disk. MongoDB also provides flexibility in the setting of write concerns. It allows users to configure the level of acknowledgement that is needed for the write operations. So as we consider MongoDB for our applications, it is crucial to keep certain factors in mind. The first and the foremost is the indexing impact. While indexes significantly improve the read performance, they can have negative impact on the write operations because each write operations need to update B+tree index. So as and when you have multiple indexes, every one thing has to be updated, and let's say each update operation is a log of n and there are t indexes per collection, so you would result in t into log of n. And if you have significant write load, this becomes super CPU intensive. And the second thing is the data modeling. The efficient data modeling, including choosing the appropriate shard keys for sharding, is very crucial to balance both the read and the write workflows effectively. If you don't have the sharding properly, you would result that your memory would increase significantly because the indexes for the shard keys are also kept in memory. And if there is significant write operations, this will go and increase the memory. Hence, you need to very much ensure that you need to have correct sharding strategy in place. And as soon as the memory increases, the lookups also will take more time and hence read performance will decrease. So let's now see what are the use case specifics for both read and the write operations. In the read optimized operations, MongoDB is often used when there is a need for querying and retrieving the data, such as the content management systems, real-time analytics, and the reporting applications. And in the write optimized world, MongoDB is used when there are high volume write operations such as logging systems or data ingestion pipelines as well. The MongoDB's ability to scale with the sharding and all and handle concurrent writes with the new storage engines makes this a suitable choice as well. So in conclusion, MongoDB is a very powerful database with features that are tailored for diverse workloads. Whether your project demands read-heavy or write-heavy operations, MongoDB's flexibility, scalability, and efficiency makes it such a solid choice. Analyze your specific requirements and make the informed decision. Remember, the knowledge that you guys gain over here is a very powerful tool in the developer's toolkit. MongoDB's versatility offers solutions for various scenarios, and mastering these features will undoubtedly elevate your database management skills. Thank you for joining me today. If you found this video helpful, don't forget to like, share, and subscribe for more content. Let me know in the comments if you have any questions or topic that you would like me to cover in the future videos. Until next time, happy learning. Bye bye.